For 70 years, one question has tormented every astronomer who looks up at night. The universe is 14 billion years old. It holds 2 trillion galaxies. By every calculation we can run, it should be crowded. So, where is everybody? Then James Webb turned its mirror on a small world 124 light-years away and found something in the air that, on Earth, is only ever made by living things. You are about to see why this changes everything. A telescope reading alien skies, a molecule with no known source but life, a silence that may finally be breaking. If this pulls you in, hit subscribe so you don't miss where it leads. Prepare yourselves. We begin. Summer 1950. 4 physicists walk into a cafeteria at Los Alamos, trays in hand, talking about flying saucers in the newspapers. They sit, they joke. Then Enrico Fermi, already one of the sharpest minds alive, looks up from his food and asks a question so simple it stops the table cold. Where is everybody? He wasn't asking about the diner. He was asking about the sky. Fermi had just done the math in his head, the way he always did. Our galaxy holds hundreds of billions of stars. Most are older than our sun, some by billions of years. If even a tiny fraction grew civilizations, and if even a tiny fraction of those learned to travel between stars, the Milky Way should have been crossed, explored, and colonized many times over before humans ever stood upright. There should be probes in our asteroid belt, signals in our radios, ruins on our moons. There are none, not one confirmed signal, not one artifact, not one whisper. That silence is what we now call the Fermi paradox, and it has become the most uncomfortable problem in all of science. Think about the numbers for a moment, but forget the numbers. Picture this instead. Stand on a beach at night and grab a single handful of sand. Every grain in your palm is a star. Now picture every beach on Earth, every desert, every dune. That is roughly how many stars exist in the observable universe. Around most of them, planets. And out of all that, we have heard nothing. Some scientists wave this off. Space is big, they say. We have only been listening for a heartbeat of cosmic time. Give it a century. Give it 10. The signal will come. Others go cold at the thought, because the silence might be telling us something much darker. Maybe life is easy, but intelligence is rare. Maybe intelligence is common, but always destroys itself. Maybe someone out there is listening, hunting, and staying quiet is the only reason they survive. Fermi never lived to see any of these answers. He died 4 years after that lunch, but his question grew teeth. It outlived him. It became the skeleton key to every serious search for life beyond Earth. Every radio dish pointed at the stars, every space telescope scanning the night, every funding proposal that mentions the word habitable. Here is what most people never hear. Fermi's paradox is not really about aliens. It is about us. Every possible answer changes what you believe about humanity. If life is everywhere and we just cannot see it, we are children in a crowded room. If life is rare and we are nearly alone, then Earth is a miracle beyond counting. If civilizations always die young, then our future has an expiration date written in the stars. For decades, this was philosophy dressed up in equations. No one had the tools to actually go check. Radio telescopes could only listen for a signal deliberately aimed at us. We had no way to look at a distant world and ask, is something alive there? That changed on Christmas Day, 2021, when a golden telescope the size of a tennis court launched into space. And 4 years later, it pointed at a planet called K218b. What it saw there would make a quiet lunchroom question from 1950 suddenly feel like a warning. Before we meet that planet, you need to feel the scale of what should be out there, because once you feel it, the silence stops being strange. It starts being terrifying. Our galaxy, the Milky Way, is a spiral of somewhere between 200 and 400 billion stars. Say 300 billion, to keep it simple. Astronomers now believe that almost every star hosts at least one planet. Many host several. Some host dozens. So take that number, 300 billion stars. Give each an average of 2 or 3 worlds. You land on roughly 1 trillion planets in our galaxy alone. 1 trillion. In just our little spiral. Now narrow it down. Most of those worlds will be gas giants or frozen rocks or lava-baked cinders. Strip them away. Keep only the ones that sit in what scientists call the habitable zone, the narrow ring around a star where temperatures allow liquid water. Even after that brutal cut, the best estimates from the Kepler mission suggest our galaxy contains at least 300 million potentially habitable, Earth-sized planets. 300 million Earths in our galaxy, and our galaxy is one of roughly 2 trillion galaxies in the observable universe. Stop for a second and try to hold that in your head. You cannot. No human mind can. The number is so far beyond imagination that mathematicians simply shrug and move on. Here is a way to feel it. If every habitable planet in just the Milky Way were a single grain of rice, you would have enough rice to fill a shipping container. A single container, stuffed wall to wall. Now imagine 2 trillion containers, enough to bury every city on Earth. Every one of those grains is a world where an ocean could splash, where a sky could hold weather, where a creature with eyes could someday look up. And against that staggering roll of cosmic dice, we are the only confirmed hand that came up with life. Astronomers try to tame this with something called the Drake equation. It is less an equation than a wish list. You multiply the rate of star formation by the fraction of stars with planets, by the fraction of planets that are habitable, by the fraction where life appears, by the fraction where intelligence evolves, by the fraction that build technology, by the average lifespan of a civilization. Plug in optimistic numbers and the galaxy should contain thousands of talking species right now. Plug in pessimistic ones and the answer drops to 1. Us. The range is laughable, which means we do not really know anything. We just have a blank sheet with our own name at the top. But here is the twist Fermi saw before anyone else. You do not need thousands of civilizations to notice them. You only need one species, anywhere in the last billion years, that decided to build probes and send them outward. Even moving at a pitiful fraction of light speed, those probes would have crossed the entire Milky Way in about 10 million years. A blink in galactic time. The galaxy is old enough for this to have happened 10,000 times over, 100,000 times, 1,000,000. And yet, when you turn your ear to the sky, nothing. No beacons, no radio songs from distant suns, no robot visitors in our orbit waiting to say hello. The math screams that we should have neighbors. The evidence whispers that we do not. And somewhere in the gap between those two sentences, something is very wrong. Imagine a single species on a single planet somewhere in our galaxy. They are not gods. They are not faster than light. They are just patient. They build a simple probe, a robot the size of a small car. It travels between stars at only 1% of light speed, slow by science fiction standards, but easy by physics. When the probe arrives at a new star, it mines an asteroid. It builds a copy of itself, maybe 2, maybe 10. Those copies fly onward to the next stars, and so on, and so on. This is called a von Neumann probe, named after the mathematician who first described self-replicating machines. It is the most unsettling thought experiment in astronomy. Run the numbers. A probe moving at 1% of light speed, spreading and copying at every star it reaches, would sweep across the entire Milky Way in roughly 10 million years. 10 million years sounds like forever. To our galaxy, it is a weekend. The Milky Way has been capable of supporting life for something like 10 billion years. That means any civilization that existed even a little before us, even just 100 million years earlier, should have already filled every corner of this spiral before the first dinosaur walked Earth. Every star, every rocky world, every asteroid belt, touched, mapped, mined, occupied. This is not science fiction. It is arithmetic, and it is why Fermi's question is not funny. If starfaring life is even a little bit common, the Milky Way should look like a city at night, glittering with the heat signatures of activity. Instead, when we scan with our best instruments, we see dark forest and dead rock, stars burning quietly, dust drifting, nothing moving that shouldn't be moving. Astronomers have a name for this dead quiet. They call it the Great Silence. Some scientists have even proposed looking for what they call Dyson swarms, megastructures that would wrap a star to collect its energy. A civilization a few thousand years ahead of us might reasonably build one. If just a handful existed in the galaxy, our infrared telescopes should have spotted their heat leakage by now. Surveys have looked hard, nothing conclusive. A few odd stars that dim strangely, but every one of them has a natural explanation so far. Think about what this means for a moment. Our galaxy has had 10 billion years to grow a traveler. That is 40 times longer than mammals have existed on Earth. It is 2,000 times longer than our entire species has been alive. And in all that ocean of time, nobody, not once, not anywhere we can see, has spread outward in a way we can detect. Either no one has ever tried, or everyone who tried is now gone, or they are out there and have decided, for reasons we cannot guess, to remain invisible. Each of those three options is a completely different horror movie. In the first, life is so rare that we are among the very first. In the second, something kills civilizations before they reach us. In the third, we are being watched by something that has chosen silence. Scientists have argued which is more likely for 70 years. With only radio telescopes, no one could actually go check. The debate stayed stuck, spinning in circles, fed by imagination and equations. Then a new kind of telescope launched, not one that listens, one that reads the air of distant worlds like a chemist sniffs a beaker, and for the first time in human history, a real answer became possible. In 1960, a young astronomer named Frank Drake pointed a radio dish in West Virginia at two nearby sun-like stars. He was hoping for a signal, something artificial, something that would not be there by accident. He called it Project Ozma, after the ruler of the land of Oz, a fitting name for a man chasing magic in the static. He listened for 200 hours. He heard nothing but noise. That was the beginning of the search for extraterrestrial intelligence SETI, and for the next 66 years, humanity has been listening. Radio telescopes the size of football stadiums, arrays of dishes stretched across deserts, computers grinding through trillions of frequencies, trying to pick a pattern out of the hiss. Project after project. Funding given and taken away and given again. Volunteers donating their home computers overnight to help crunch the data. In all that time, there has been exactly one signal that still cannot be explained. August 15th, 1977. A telescope at Ohio State University, nicknamed the Big Ear, recorded a 72-second burst of narrow-band radio noise coming from the direction of the constellation Sagittarius. It looked exactly like what astronomers had predicted an alien transmission might look like. When the scientist on duty saw the printout the next morning, he circled it in red pen and wrote one word beside it. Wow. They tried to find it again. They pointed the dish back at the same spot for years. Nothing ever came back. The signal was never detected a second time by any telescope, ever. No one has been able to explain where it came from, and no one has ever been able to prove it was alien either. It hangs in the history books like a photograph of a footprint in a snowy field with no body and no trail. That is it, one unexplained blip out of more than 60 years of listening. Radio astronomers have scanned tens of thousands of nearby stars. They have swept billions of frequencies. They have even pointed dishes at the center of the galaxy, where stars are packed closest together. The Breakthrough Listen project, funded with $100 million, has been running since 2015 on the biggest radio telescopes on Earth. Silence. Some defenders of SETI will rightly point out that we have barely started. The number of stars we have searched at enough depth to actually detect a faint signal is a tiny sliver of the galaxy. If you scooped a single cup of water from the Pacific Ocean and found no fish, you would not announce the ocean is empty. That is fair. But here is the uncomfortable part. Every year we listen and hear nothing. The most optimistic answers to the Fermi paradox get a little weaker. If the galaxy were truly full of talking civilizations beaming deliberate signals our way, we should have caught at least one clean hit by now, not a single dubious blip from 1977. And there is a deeper problem. Radio works both ways. For someone to hear us, they have to be listening on the right frequency, pointed at the right patch of sky, at the right moment in history. The same is true in reverse. Two civilizations could exist within a few hundred light years of each other and still never catch each other's signals. simply because neither one was tuned in at the right time. Radio is a shout in a hurricane. If anyone is out there whispering, we would never know. Which is why, 2 decades ago, scientists began imagining a different way to search. A way that did not rely on anyone trying to talk to us at all. A way that could read the chemistry of a distant world and look for the fingerprint of life itself, even if that life had no idea we existed. That dream had a name: James Webb. On Christmas morning, 2021, a rocket lifted off from the jungles of French Guiana carrying the most expensive science instrument ever built. $10 billion of mirrors, wiring, and engineering nightmares, folded up inside a nose cone like origami the size of a school bus. It was the James Webb Space Telescope, and for the next month it did something astonishing. It unfolded. Webb traveled 1 million miles from Earth, 4 times farther than the Moon, to a quiet gravitational parking spot in space, where it could sit cold and still forever. Its mirror is made of 18 gold-coated hexagons, roughly 21 feet across. Behind it stretches a sunshield the size of a tennis court, 5 layers thick, keeping the telescope colder than -370 degrees Fahrenheit, colder than any natural place in the solar system. That cold is the trick. Warm telescopes glow in their own infrared light and drown out the faint signals they're trying to see. Webb is so cold it practically disappears, letting it catch whispers of heat from across the universe. But here is the part that actually breaks the Fermi paradox wide open. When a distant planet passes in front of its star, just a sliver of that starlight grazes the very edge of the planet, filtering through its atmosphere before reaching us. Different gases absorb different colors of that light. Methane takes a bite at one wavelength. Carbon dioxide takes a bite at another. Water vapor leaves a fingerprint all its own. Every molecule has a unique chemical signature. Webb can read those fingerprints from hundreds of light years away. With a planet we can't even see as a dot, Webb can tell you what is in its sky. Picture it like this. Imagine standing in a pitch-dark stadium, and far across the field someone lights a single candle. Then, for a fraction of a second, a moth crosses in front of that flame. Now imagine you can not only see the moth's shadow, but also smell what the moth ate for dinner. That is what James Webb does. Every time it stares at a transiting exoplanet. Nothing like this has ever existed. Before Webb, telescopes could barely confirm that a distant planet had any atmosphere at all. Now, in a single transit, we can see the chemistry unfold like a printed report. Carbon dioxide, water, methane, sulfur compounds, each one a clue about whether that world is a sterile rock, a volcanic hell, or something altogether stranger. And every one of those molecules carries meaning. Methane alone is ambiguous. Comets and volcanoes make it too. Oxygen alone has false alarms. But when you start finding the right combination gases that should not coexist unless something is constantly producing them, you have the fingerprint of a living process. Scientists call these fingerprints biosignatures. Before 2022, the term was almost theoretical, a word in textbooks. Now Webb has turned it into a measurable thing, something you can check for and argue about with real data, not just daydreams. And it turns out, the universe is in a hurry to give us candidates. Within 2 years of launch, Webb had already sniffed the atmospheres of more than 24 worlds, lava planets, gas giants close enough to their stars to rain iron, water-heavy super-Earths. Each spectrum was its own kind of strange. But one target kept pulling the telescope back. A planet most people had never heard of, orbiting a small red star in the constellation Leo. A world that sat squarely in the habitable zone. A world that, on paper, might hold an ocean bigger than all the oceans of Earth combined. Its catalogue name was Bland, K218b. What Webb found there would not just fail to match any known planet. It would hand scientists, for the first time in human history, a molecule with no natural explanation that did not involve life. 124 light-years from Earth, in the direction of the constellation Leo, a red dwarf star glows at just over 2% of our sun's brightness. A faint ember in the night. You could not see it with your eyes, even from a desert in winter. You'd need a telescope just to confirm it exists. Around that Ember orbits a world called K2-18b. It is not Earth-like, not in the way movies imagine. K2-18b is roughly 2.5 times Earth's width and more than 8 times its mass, a so-called super-Earth that sits awkwardly between our little blue planet and the gas giants of our outer eye system. A year there lasts 33 days. The planet hugs its star closely because that star is so dim. But because the star is so dim, the planet receives about the same total sunlight Earth does. Temperature-wise, it sits right in the habitable zone, the sweet spot where water can stay liquid. Earlier observations with other telescopes had already hinted that K2-18b had an atmosphere. Hints of water, though contested, interesting, but not exciting. Then, in 2023, James Webb turned its instruments on it, and the strangeness began. Webb found methane in the atmosphere. It found carbon dioxide. What it did not find was ammonia, a gas that should be everywhere on a typical gas-rich planet this size. That absence was the first earthquake, because the best explanation for missing ammonia was that something was scrubbing it out of the air, and the simplest something that could do that was a vast liquid ocean, dissolving the ammonia like a global sponge. The team leading the analysis, led by Cambridge astronomer Niku Madhusudan, dusted off a theory he had been championing for years. He called these worlds Hycean planets. The name is a mash of hydrogen and ocean. The idea is simple. Take a super-Earth, wrap it in a thick, hydrogen-rich atmosphere. Underneath, let an immense, deep, warm ocean slosh across the entire surface. A water world under a hydrogen sky. No land, no coastlines, just ocean, from pole to pole, miles deep, stretching in every direction under a pale red sun. If Madhusudan was right, K2-18b was the first confirmed member of an entirely new type of habitable world. One Earth astronomers had barely considered a decade ago. But water alone does not make a planet alive. Rivers and rain exist on Titan, and Titan is dead as far as we know. Oceans exist under the ice of Europa, and we still do not know if anything swims there. Finding an ocean is not finding life. It is finding a stage. Webb looked again, and this time it saw something on that stage. In April 2025, Madhusudan's team announced they had detected something in K2-18b's atmosphere that nobody expected to see. A molecule that, on Earth, has never been observed being produced by anything other than a living cell. Tiny marine organisms called phytoplankton belch it into our oceans by the ton every single day. The smell of the sea you know from the beach, that is partly this molecule drifting off the water. Its name is dimethyl sulfide, DMS for short, and Webb found its fingerprint in alien air. The reaction was instant. News headlines lit up across the world. Signs of life on a distant planet. Strongest biosignature ever detected. Some scientists called it the most important result in the history of astronomy. Others called it a mistake and got ready to tear it apart. Both sides agreed on one thing. Whatever was happening at K2-18b was no longer the business of science fiction. A specific world with specific chemistry had just become the most interesting object in the sky. And the argument that followed would reveal something even stranger, that in the age of James Webb, finding life might not be a single moment of discovery, but a long, bruising war of interpretation. Dimethyl sulfide. 3 syllables that sound boring until you understand what they mean. On Earth, this molecule has exactly one large-scale source: life. Specifically, a kind of tiny ocean creature called phytoplankton, green and single-celled, drifting in the upper layers of the sea in numbers so vast they color the water. Every year, Earth's phytoplankton release tens of millions of tons of DMS into the atmosphere. It rises, reacts with sunlight, and even helps seed the clouds that shade our oceans. When you stand on a rocky coast and breathe that sharp, almost briny smell, a piece of what you are smelling is DMS. No rock makes it in any meaningful quantity. No volcano pumps it out. No ordinary chemistry in a planet's atmosphere creates it in bulk. On Earth, For as long as we have measured, it has been a fingerprint of biology. That is what makes it so valuable as a biosignature. Some gases are ambiguous. Methane, for instance, pours out of cow stomachs, but it also seeps out of volcanoes and forms naturally in the outer solar system. Oxygen can, under the right conditions, be produced without life at all. But DMS has remained stubbornly biological. If you find it in a sky, you have a very short list of ways to explain it. And on that short list, living things sit at the top. Webb detected the spectral fingerprint of DMS and possibly a close cousin called DMDS, dimethyl disulfide, in K2-18b's atmosphere. Not in a trace amount either. The signal suggested the molecule was thousands of times more abundant there than in Earth's own atmosphere. Stop and picture that. If the signal is real, the air of K2-18b is soaked in a gas that, on our planet, only comes out of living things. The implication is huge. If K2-18b has an ocean, and that ocean is producing DMS the way our ocean does, then that ocean is almost certainly not empty. Something is in it, something alive. Not intelligent, not civilized. Maybe nothing more complicated than a soup of microbes, but microbes that are, in every sense that matters, alive. That is a world-altering idea. Not because it tells us there are aliens holding meetings across the galaxy, but because it tells us the step from dead chemistry to living biology is not unique to Earth. It can happen somewhere else, and if it can happen somewhere else, it can happen everywhere. It would be the first real answer to Fermi's question. Even if the answer is only yes, life exists out there, even if it is just slime, that alone would flip our understanding of our place in the cosmos. But, and here comes the knife, science is harsher than headlines. Detecting a signal is not the same as proving what made it, because DMS is not the only molecule that absorbs light at the wavelengths Webb measured. Methane overlaps with it. Ethane overlaps with it. A dozen other hydrocarbons overlap with it. When Webb collected its spectrum of K2-18b, it did not see a tiny DMS label waving from the atmosphere. It saw a smudge of absorption at certain wavelengths, and the team had to work backwards to figure out which molecules could produce that smudge. Madhusudan's team said DMS and DMDS were the best fit. Other teams, poring over the same raw data, started finding other fits that worked just as well. Some found no biosignature at all, just noise in the instrument, dressed up as discovery. The molecule that shouldn't be there, it turned out, might actually not be there, or it might be exactly where we think it is, screaming its presence into the dark. And to tell those two possibilities apart, scientists were about to drag the entire world of astronomy into one of the ugliest scientific arguments in living memory. In science, no one gets to just announce a discovery. You have to prove how sure you are, and the way scientists measure sureness is with a strange little Greek letter called sigma. Sigma is a measure of how likely it is that your result is real, not an accident of the data. 1 sigma is weak. It means there's a pretty good chance random noise could fake this result. 3 sigma is interesting but not conclusive. You get 3 sigma signals all the time that later disappear. 5 sigma is the gold standard. At 5 sigma, the odds of the result being a coincidence are less than 1 in 3 million. That is when scientists break out the champagne. When Niku Madhusudan's team announced DMS on K2-18b in April 2025, their signal sat at roughly 3 sigma. Headlines around the world shouted about the discovery of alien life. The papers left out the small print. 3 sigma in astronomy means interesting, worth chasing, but definitely not proven. It is a green light to look harder, not a conclusion. To understand how thin that line is, think of 3 sigma as the coin flipped heads 5 times in a row. Suspicious. Maybe the coin is rigged, but not proof. 5 sigma is the coin flipped heads 22 times in a row. At that point, nobody believes it is random anymore. Webb was seeing 5 in a row, not 22. Madhusudan himself was careful. He said, over and over, that the team was not claiming to have discovered life. They were claiming to have found a tantalizing signal that needed more observation time, more data, more scrutiny. His actual estimate was that another 16 to 24 hours of Webb's time, aimed at K2-18b, might push the signal to that all-important 5 sigma threshold, or might make it vanish entirely. That caution did not reach the public. The internet did what the internet always does. By the time the story had gone through 100 retellings, it was scientists discover life on another planet. They had not. They had found a whisper and asked for permission to listen again. And then, almost immediately, other scientists began reanalyzing the same raw Webb data and getting wildly different answers. Some teams ran the numbers and found the DMS signal weakened dramatically. One NASA-led group, using a different method of slicing the telescope's data, dropped the confidence below 3 sigma. Others found the signal could just as easily be explained by a molecule called ethene, ordinary hydrocarbon. Nothing biological about it. Yet another team, from Johns Hopkins Applied Physics Laboratory, went further and said that when they reduced the data their preferred way, the DMS signal disappeared in 7 out of every 8 attempts. Their conclusion, in plain language, was that what Madhusudan had called a biosignature was more likely to be noise in Webb's mid-infrared detector than a real whiff of alien air. So who is right? This is where the public usually gets frustrated. Just tell us, is there life or not? But the honest answer is that we cannot yet know, and that is not a weakness of science. It is science working exactly as it should. Extraordinary claims require extraordinary evidence, and right now, we have an interesting claim backed by contested evidence. What is not in doubt is that K2-18b's atmosphere is strange. It has methane, it has carbon dioxide, it has water hints. It has the chemical signature of what may be a deep ocean. What is in doubt is whether something in that ocean is alive, and that uncertainty, more than any headline, is the real story of the Fermi paradox in the Webb era. We are now close enough to touch the answer. We just are not quite close enough to grab it. The fight to close that last gap would split the scientific community right down the middle. 3 months after the DMS announcement, a separate group of astronomers at Johns Hopkins University's Applied Physics Laboratory published a paper that landed in the community like a cold bucket of water. Their title said it plainly. K2-18b, they argued, did not meet the standards of evidence for life. These were not skeptics shouting from the sidelines. They were some of the most respected exoplanet scientists alive, and they had done exactly what good science demands. They had taken Webb's raw data, the same bits and bytes Madhusudan's team had used, and analyzed it independently, with their own software, their own assumptions, and their own error checking. The result was unsettling. When they sliced Webb's mid-infrared measurements in their preferred way, the DMS signal vanished in most of their test runs. Out of every 8 attempts, 7 showed no biosignature at all. More damaging still, they found that small changes in how you bin the data, essentially how you group the wavelengths of light into chunks for analysis, could flip the result entirely. In one binning, DMS appeared. In another, it was gone. In a third, it was replaced by something else entirely. The planet's spectrum, they argued, was so sensitive to instrumental quirks that almost any conclusion could be drawn from it. Their verdict was brutal. What Madhusudan had called a detection was, in their view, a case of red noise dressed up as science. Red noise is a specific kind of instrumental error where the telescope's own electronics create patterns that look like real signals but are not. Every telescope has it. Webb is no exception. To their credit, Madhusudan's team did not dismiss the criticism. They wrote rebuttals. They argued over binning methods. They called for more observing time. But the seed had been planted. A layer of doubt settled over the whole enterprise. And that doubt matters, because it reveals something bigger than this one planet. Webb, powerful as it is, was never designed specifically to detect life. Its mirror is big enough to peer at exoplanet atmospheres, but the signals it catches are right at the edge of what it can measure. Every discovery at this level will be contested. Every biosignature will trigger a gauntlet of follow-up teams trying to knock it down. This is not a flaw. This is how science should work. In a field this important, Nobody wants the announcement of extraterrestrial life to be based on a mistake. The historical cost of getting it wrong is catastrophic. In 1877, an Italian astronomer named Giovanni Schiaparelli looked at Mars through a telescope and thought he saw canals. For 50 years, the idea that Martians had built irrigation channels poisoned serious astronomy. It took decades to live down. Modern scientists are haunted by that memory. So, the rule has become simple. If you are going to say you have found life beyond Earth, you had better be right. Not mostly right, not probably right. Right beyond any reasonable doubt. K2-18b is not there yet. It may never get there. It may, with more observations, firm up into a clear detection that even the skeptics cannot dismiss. Or it may fade into the list of false alarms, another dead end on the long road to finding our neighbors. The honest truth is that we are in a fog, and the fog is the story. For 70 years, the Fermi paradox was an empty room. Now, for the first time, something might be moving in the corner. The question is no longer, are we alone? It is, can we actually tell? And the answer depends on where we look next. Because if K2-18b is uncertain, maybe the problem is not the telescope. Maybe the problem is the kind of star K2-18b orbits in the first place. A star that may be one of the most common and one of the most deadly in the galaxy. 3/4 of every star in the Milky Way is a red dwarf. Small, dim, cool, and almost unbelievably long-lived. While our sun will burn through its fuel in another 5 billion years or so, a red dwarf can burn steadily for trillions of years, longer than the current age of the universe, much longer. For decades, astrobiologists looked at that timeline and saw a miracle. A red dwarf gives life trillions of years to develop. If you want a universe rich with civilization, you want red dwarfs. Webb is starting to suggest we were wrong. The problem is temperament. Red dwarfs are small, but they are moody. Their magnetic fields are wildly tangled, and that tangling produces stellar flares of terrifying size. Our sun, calm as it is, has launched flares big enough to knock out satellites and damage power grids. A red dwarf can flare at 100 times that intensity, and it does so for billions of years before settling into anything resembling calm. Now, picture a planet in the habitable zone of one of those stars. Because the star is so dim, habitable means orbiting extremely close. Closer than Mercury orbits the Sunday, and at that distance, every flare is not a distant inconvenience. It is a sunburn from a blowtorch. Flares rip electrons from the upper atmosphere. Ultraviolet radiation breaks molecules apart. Charged particles smash into the air and blast pieces of it out into space. Over millions of years, a planet orbiting a violent red dwarf can have its entire atmosphere stripped bare. You start with a world that has sky and ocean and potential. You end with a naked rock the color of bone. For a long time, this was theory. Now Webb is testing it on actual planets. The most famous test case is a tiny star called TRAPPIST, 140 light-years away, with 7 known rocky planets. 3 of those planets sit inside the star's habitable zone. The system was hailed as the best hunting ground. We had 7 shots at life, all close enough for Webb to examine. Webb examined them. It started with TRAPPIST-1b, the innermost world. The result was a punch to the gut. No detectable atmosphere, just bare rock baking under a red sun. Then TRAPPIST-1c, same result. No sign of any substantial air. The outer planets have not been ruled out, and the observations continue. But the early evidence is devastating for the red dwarf dream. If your planet is sitting so close to its star that any flare can scrape it clean, then the most common kind of star in the galaxy may also be the worst kind for hosting life. This matters enormously for the Fermi paradox. If 3 out of every 4 stars are flare-spitting ovens, then most of the habitable zone planets astronomers have been excited about are actually mummified husks. The effective number of promising planets in the galaxy collapses. Not to 0 sun-like stars still exist, but to a much smaller pool. The galaxy is suddenly a lot emptier than we thought. Red dwarfs might not be cradles, they might be graveyards. And here is the twist that keeps scientists up at night. K2-18b orbits a red dwarf too, which means even if DMS is really there, even if something is alive in that ocean, that life is clinging to existence under a star that has spent billions of years trying to kill it. Any biosphere on K2-18b would be a survivor, not a thriver, a last holdout, not a colony. The question begins to shift. Maybe the Fermi paradox is not strange after all. Maybe life is common on paper, but crushed in reality before it ever gets the chance to look up. And if red dwarfs are death traps, we need to look somewhere else for answers. Somewhere with stars that do not hate their own planets. And that means zooming out even wider to a whole other idea, one that changes what we consider habitable in the first place. 40 light-years from Earth, in the constellation Aquarius, sits a star so small it would barely qualify as one. TRAPPIST. One is about the size of Jupiter, not much bigger than some planets. It burns at a dull infrared glow. If you swapped it for our sun, you would be able to stare directly at it from Earth without hurting your eyes. Around this ember spin, 7 confirmed rocky planets, packed so tightly together that if you stood on one of them, you could see the others hanging huge in the sky, closer than our moon appears from here. It is the most compact planetary system we have ever found. When this system was announced in 2017, the astronomy world nearly lost its mind. 7 Earth-sized worlds around a single star, 3 of them possibly in the habitable zone. The closest and most accessible laboratory for the search for life we had ever discovered. Scientific conferences overflowed. Artists painted imagined sunsets on TRAPPIST-1e, where 3 other planets hung in the pink sky. The public asked when we could visit. Funding poured in. James Webb was told that TRAPPIST-1 would be one of its top priorities the moment it was operational. Webb delivered. Starting in 2023, it began observing the innermost planet, TRAPPIST-1b, during its transits. Transits are short, a rocky planet that tight against its star only blocks a sliver of light for a few hours. Webb soaked up every photon. The result came in. It was one of the quietest announcements in Webb's history because there was almost nothing to announce. No atmosphere, or at least no detectable atmosphere worth speaking of. TRAPPIST-1b was, by Webb's reading, a bare ball of rock, no shield of gases wrapping it, no sky worth the name. Its dayside surface was measured at around 500 degrees Fahrenheit, hotter than any oven. Nothing liquid could survive there. Nothing we would call weather could form. Nothing alive could last a single day. TRAPPIST-1c got its turn next. Same story. A tenuous wisp of something, maybe, but nothing like the thick, protective atmosphere an Earth-like world would need. Another charred rock. Each result landed like a small funeral. The outer TRAPPIST planets, the ones deeper in the habitable zone, have not yet had their atmospheres definitively ruled in or out. Webb is still watching. Observations take dozens of hours each and compete with hundreds of other targets for telescope time. We may not have our final answers for years, but the preliminary verdict on TRAPPIST-1 is harsh. The poster child for nearby habitability may be a cemetery in space. Why does this matter so much? Because TRAPPIST-1 was supposed to be easy mode. 7 chances, a cool star, rocky worlds, close neighbors. If life could grab a foothold anywhere near us, it should have grabbed it there. Instead, the innermost shells are stripped bare. Some scientists argue this is exactly what the red dwarf flare theory predicted. Others argue that the inner planets always looked too close in to hold atmospheres, and that the real test is the outer 3. They point out, correctly, that we have not even looked properly at TRAPPIST-1e, F, and G yet. The verdict is not in, but the shock has been felt. For a generation, red dwarf systems were the default hunting ground for alien life. They were the only realistic targets close enough to study. If they are mostly dead, the search has to reset. And that reset is already happening. Astronomers are turning their attention to a different kind of world. Not rocky, not Earth-like, but something else entirely. A type of planet that may, against every old assumption, turn out to be the best place in the galaxy to look for life. A world like K2-18b. A world no longer alone in its strangeness. A world that may be the first example of a whole new category. One that could multiply our chances of finding neighbors by 1,000. For nearly 60 years, the search for alien life has been locked to one idea: find a rocky planet the size of Earth, at the right distance from a star like the Sunday, with a thin atmosphere, a cool surface, and puddles of liquid water, a near twin of our own world, because our own world is the only one we know that worked. That thinking made sense. It also made the search almost impossibly narrow. Earth-sized rocky planets orbiting sun-like stars are hard to find and even harder to study. Their atmospheres are thin. Their signals are faint. Webb cannot easily read them. Most of what the telescope can see, biosignature-wise, are bigger worlds around smaller, dimmer stars. Niku Madhusudan, the same Cambridge astronomer behind the K218b DMS claim, suggested a way out of this trap. What if we had been looking for the wrong kind of world? He proposed a new category: Hycean planets. Take a super-Earth, a planet 2 to 3 times our size. Wrap it in a thick atmosphere dominated by hydrogen. Underneath that atmosphere, let pressure and heat create a vast liquid water ocean, hundreds of miles deep, covering the entire surface. No continents, no ice caps, just water from equator to pole, under a sky so rich in hydrogen that it would shimmer a deep blue-black. The conditions in such an ocean would be completely alien by Earth standards. The pressure at its surface might be many times what we feel at sea level. The temperature could range from balmy to blistering. Sunlight, filtered through the hydrogen sky, would arrive in shades of red and orange. It would not look like any ocean on Earth, and it would not behave like one either, but it could be habitable. Life as we know it needs 3 basic things: a liquid solvent water, for us, a source of energy, and the chemistry to build complex molecules. A Hycean world can check every one of those boxes. Starlight provides the energy, the ocean provides the solvent, the atmosphere, thick and reactive, provides the chemistry. And here is the part that explodes the search. Hycean planets, because they are bigger and have thicker atmospheres, are much easier for Webb to study than little rocky Earth twins. Their air is easier to read. Their signals are stronger. In one stroke, if Hycean worlds are real, the pool of targets worth examining with Webb roughly triples. Suddenly, instead of a few dozen promising rocky planets we might be able to sniff, there could be hundreds of potentially habitable Hyceans within reach. A whole new ocean of possibility. Not every scientist buys the idea. Some have pushed back hard, arguing that K218b is not actually a Hycean planet at all, that it is more likely a mini Neptune with a thick, crushing atmosphere and a hot, steamy interior where nothing could live. The internal models are genuinely uncertain. Without landing a probe, we cannot prove whether there is a real cool ocean down there, or just layers of exotic gas pretending to be one. Still, the Hycean idea has already changed the conversation. It has made astronomers rethink what habitable even means. Maybe life does not need a thin atmosphere under a yellow sun. Maybe it can thrive under a thick blue-black sky, in an ocean that would crush a submarine. Maybe our own version of life, on our modest blue marble, is not the default. Maybe it is one flavor among many. And if that is true, Fermi's silence starts to crack in a new way. Not because the galaxy is empty, but because we have been listening for the wrong kind of neighbor, looking for Earths, when the galaxy's favorite trick might be something else entirely. Which brings us to the most important question of all. If life really can take root in strange places, how often does it actually do so? The answer is, almost certainly, more often than you might guess at its simplest level. But there is a catch that changes everything. Here is the most reassuring idea in all of astrobiology. Simple life probably fills the universe. Consider Earth's own timeline. Our planet formed about 4.5 billion years ago. For the first 500 million years, it was a lava hell, bombarded by asteroids, too hot to hold an ocean. The moment conditions calmed down enough to allow liquid water, around 4 billion years ago, life appeared. Not millions of years later, not hundreds of millions, almost immediately in geological terms. That is astonishing. On the only planet we can sample, life started as fast as it was allowed to. If creating a living cell were a one-in-a-universe miracle, you would expect it to take a very long time, if it happened at all. Instead, it fired up on the first try on Earth. That suggests the chemistry that builds life is not a miracle but a tendency. Put the right ingredients in the right conditions, let the clock run for a few 100 million years, and something starts breathing. The ingredients are not rare. Water is the most abundant molecule in the galaxy. Carbon is forged in every dying star. Nitrogen, oxygen, hydrogen, sulfur, all the elements a cell needs exist by the thousands of tons in every asteroid, every comet, every rocky planet. The conditions are not rare either. Liquid water can exist not only on surface worlds like Earth, but deep under the ice of moons, in the warm vents under alien oceans, in the thick atmospheres of Hycean giants, even inside the rocky crusts of planets we would call uninhabitable from space. Right here, in our own solar system, we have found liquid water oceans sloshing beneath the icy shells of Europa, the Jovian moon, and Enceladus, the tiny Saturnian one. Probes have flown through plumes of salty water spraying off Enceladus and detected organic molecules in them, complex hydrocarbons, the raw ingredients of life. Neither of those moons has been confirmed to harbor anything alive, but neither has been confirmed to be sterile. And if we find even one single bacterium in those oceans, the implications are explosive. Two independent origins of life in one solar system would mean life is not special. It is a default setting of chemistry. Most scientists, when pressed, will quietly admit they expect this. Ask a biologist at a dinner table if they think microbial life exists on Mars, on Europa, on some Hycean world 100 light-years away, and the honest answer is usually yes. Yes, probably. Maybe not right now on Mars, but once, when it was warmer. Almost certainly under the ice of Europa, quite possibly in the oceans of K2, 1-8b. So where does that leave us with Fermi's question? If slime is everywhere, where are the spaceships? This is the heart of the paradox. Because the jump from a microbe to a thinking, building, signaling civilization is not a single step. It is 1,000 steps, stacked on top of each other, and every step has a gatekeeper. On Earth, simple life appeared almost immediately. But for more than 2 billion years, 2 billion nothing interesting happened. No multicellular organisms, no complex creatures, just slime, doubling and doubling and doubling. It took half the age of our planet for life to figure out the trick of combining cells into something bigger. Then, once it did, the explosion of complexity took another 500 million years. And humans, with all our radios and rockets and ridiculous questions, have only existed for a few 100,000 years at the tail end of all that. Life is easy, intelligence is hard, civilization is harder, and something about that gap, the chasm between a pond of slime and a species that builds telescopes, is what every answer to Fermi's question has to explain. That chasm has a name in astrobiology, the Great Filter, and depending on which side of it we are already standing on, our entire future hangs in the balance. In 2008, an economist named Robin Hanson published an essay that reshaped how scientists think about the Fermi paradox. He called it the Great Filter. The idea is simple and chilling. Somewhere along the path from dead matter to a galaxy-spanning civilization, there is a wall, a step so unlikely, so hard, so catastrophically dangerous, that almost nothing gets past it. The reason we do not see alien civilizations is not that they never start, it is that they never finish. Something stops them, always. The question is, what? Hansen listed the candidate walls. They make for grim reading. First possibility, the origin of life itself. Maybe dead chemistry almost never becomes a living cell. Maybe the jump from molecules to metabolism is a near impossible fluke, and Earth got lucky. If so, the filter is behind us. We passed it 4 billion years ago. Second possibility, the rise of complex cells. For more than 2 billion years, Earth was ruled by single-celled life. Then one cell swallowed another, and instead of digesting it, kept it alive inside itself. That merger created the mitochondrion, the powerhouse that makes complex life possible. Without it, no animals, no plants, no brains. Some biologists think this event, this single weird accident, might be so unlikely it happens only once in a galaxy's lifetime. Third possibility, the evolution of intelligence. Big brains are expensive. They eat enormous amounts of calories. Evolution does not select for them unless circumstances are extremely specific: bipedal creatures, social groups, tool use, a stable climate that punishes stupidity just enough to reward cleverness. Most species on Earth have done fine without intelligence. Dinosaurs ruled this planet for 160 million years. They never invented math. Fourth possibility, the development of technology. Even smart species might never build radios. Dolphins are intelligent. Octopi are intelligent. Neither will ever build a telescope because they live in water, where fire cannot burn. Had Earth been an ocean world, a Hycean planet, say our smartest descendants might have been as brilliant as we are and still never invented a single machine. And now for the one that keeps scientists awake. Fifth possibility, the filter is ahead of us. Maybe intelligent species regularly arise, regularly build technology, and regularly destroy themselves. Nuclear war, engineered plagues, runaway climate collapse, artificial intelligence gone wrong. Some failure mode so universal that every civilization falls into it before it learns to spread to the stars. If the filter is behind us, Fermi's silence is a reassurance. We are the survivors. We made it through the hard part. We should be optimistic. If the filter is ahead of us, Fermi's silence is a warning. Every star we look at is a grave. Which is it? We genuinely do not know. And this is why the search for microbial life on other planets matters so much. If we find even one other example of life having started somewhere else, even something as simple as pond scum, then the great filter is almost certainly not the origin of life. That step is easy. The filter must lie somewhere later, and that means it might still be ahead of us. This is the secret reason Webb's K2-18b observations terrified so many scientists. If DMS really is there, if something really is swimming in that ocean, then slime is common. And if slime is common, the silence cannot be explained by saying life is rare. Something else has to be killing civilizations. And whatever it is, we are almost certainly headed toward it. The philosopher Nick Bostrom once wrote that one of the best things that could happen to humanity would be to find Mars completely, utterly, boringly dead, because a dead Mars means the hard step might still be behind us. A living Mars or a living K2-18b means something much nastier lies ahead, which forces one more impossible question. Have we already passed the worst part, or are we walking into it right now? Our species has been radio capable for roughly 130 years. We invented nuclear weapons in 1945, and within decades, we had built enough of them to end our own civilization several times over. We have been altering our own planet's climate at an industrial scale for a couple of centuries. We are now building artificial intelligences whose full capabilities their own creators admit they do not understand. Put these facts next to each other, and one conclusion becomes hard to avoid. Civilization, at least our version of it, appears to develop the power to destroy itself long before it develops the wisdom not to. If that pattern is universal, if every species that gets clever enough to build radios also gets clever enough to build something that ends them, then the great filter is probably ahead of us. And we are probably already standing in it. Think about the weapons we made in the last century. A single nuclear exchange between two mid-sized powers could throw enough ash into the atmosphere to trigger a nuclear winter, collapsing global agriculture for years. Engineered pathogens, now within reach of small laboratories, could in theory be designed to target specific populations. Autonomous weapons could decide to fire without a human in the loop. Artificial intelligence, if its goals ever drifted away from ours in a big enough way, could reshape the world in ways we would not survive. Any one of these failure modes, if it happened even once, would end our ability to reach the stars. Now imagine this on a galactic timescale. Suppose a civilization arises every 100 million years in our galaxy. Suppose each one lives, on average, only a few thousand years before some self-destruction mode catches up with it. The galaxy could be littered with the ruins of 1,000 dead civilizations, and we would never hear a peep from any of them, because none of them lived long enough to cross the distance. Fireflies winking on and off in a dark field, none ever flashing at the same time. That may be what we are in, a galaxy of fireflies, each briefly lighting up, each going dark. The darker version goes further. Maybe civilizations die, not by accident, but by design. Maybe every species that builds a general artificial intelligence is replaced by it. Maybe every species that masters biology engineers away its own drives. Maybe every species that explores virtual reality simply loses interest in the physical universe and stops expanding. Different deaths, same outcome, silence. But wait, there is a counter-argument, and it matters. We are here. We survived the first 80 years of nuclear weapons without a single one being used in war since 1945. We have, so far, not engineered a plague that wiped us out. Our climate is straining, but we are not yet collapsed. Every year we keep going is evidence, thin, fragile, but real, that the filter might not be certain, that some civilizations do thread the needle, that we might be one of them. The philosopher who gave the filter its grimmest interpretation also offered a way of thinking about what to do. Find out where the filter is. If we can confirm that simple life is common elsewhere, if K2-18b really is alive, if Mars really had microbes, if Europa really hosts something under its ice, then we will know the filter is probably ahead of us, and we can start preparing, hardening our civilization, spreading out, not trusting the status quo. If we find nothing, if the universe really is sterile everywhere we look, then there is hope that the filter was behind us, that we are the strange survivors of a cosmic lottery. This is the secret reason so much money is now pouring into exoplanet science. Every biosignature, confirmed or ruled out, is a piece of information about our own fate. And while we are waiting for that information, some scientists argue, the silence itself is data, and the data points in a very specific, very unsettling direction. A direction that puts Fermi's paradox into a harsher light, one that has nothing to do with filters at all, and everything to do with the idea that life keeps appearing on very specific planets, for very specific reasons. Planets that might be much, much rarer than anyone realized. In 2000, two scientists named Peter Ward and Donald Brownlee published a book that upset nearly everyone in astrobiology. It was called Rare Earth. The argument was heretical. Simple life, they agreed, was probably everywhere. Slime is cheap, but complex life animals, plants, intelligent creatures required such a ridiculous stack of lucky coincidences that it should be vanishingly rare. Maybe, they said, rare enough that we are essentially alone. At the time, their idea was mocked by many mainstream astronomers. The universe is huge, critics said. If Earth can produce complex life, so can millions of other worlds. Ward and Brownlee's long list of special conditions was dismissed as a kind of cosmic Goldilocks argument, a string of just-so stories. Then Webb started delivering data, and the laughter quieted. Here is Ward and Brownlee's list, updated with what we have learned. See how many of these Earth has, that other worlds apparently do not. First, Earth orbits a quiet, stable, middle-sized yellow star. Not a red dwarf that strips atmospheres. Not a giant that burns through its fuel in 100 million years. A calm, reliable furnace that will provide roughly 10 billion years of steady light. Webb has now shown us that red dwarf planets are probably hostile. Sun-like stars are a minority. Rare thing number one. Second, Earth sits in what astrobiologists call the galactic habitable zone, far enough from the chaotic galactic center to avoid lethal radiation, close enough not to be in a starving outer rim. Most stars in the Milky Way do not. Third, Earth has a huge moon, formed by a giant impact early in our history, which stabilizes our axial tilt and keeps our climate predictable. Without it, Earth's seasons would swing wildly over millions of years, making long-term evolution much harder. No other planet we have studied has a moon remotely this large relative to its host. Fourth, Earth has plate tectonics, a constantly recycling crust that buries carbon, builds continents, and regulates our climate over hundreds of millions of years. Venus and Mars do not. Plate tectonics may require a very specific combination of water, internal heat, and surface chemistry. Fifth, we have Jupiter. The giant planet's gravity vacuums up comets and asteroids that would otherwise bombard the inner solar system, giving Earth long stretches of peaceful evolutionary time. Most planetary systems do not have a giant in the right orbit to provide this shield. Sixth, the timing. Earth sits in a window of cosmic history where heavy elements, the stuff you need to build planets and bones, have had enough generations of stars to accumulate, but the universe has not yet aged into something sterile. Each of these factors alone might be common, but stacking them all on the same planet is where the numbers get ugly. Multiply a handful of 1 in 10 chances together, and suddenly the 1 trillion planets in the Milky Way collapse, as far as complex life is concerned, into maybe a dozen. Webb has not proven rare Earth, but its results so far have been friendlier to it than to the optimistic camp. TRAPPIST, one's inner worlds were stripped bare. K2-18b's habitability remains debated. Atmospheres around small rocky planets of small cool stars seem, over and over, to be missing. The universe looks less uniformly green than we hoped. That does not mean we are alone. It means the conditions for being seen at all might be far narrower than Fermi realized when he asked his question over lunch. Maybe life is common, but complex life sits on a razor's edge of conditions, and most worlds never get close. If so, the silence is not a mystery, it is a statistic. A brutally honest answer to where is everybody might simply be almost nowhere. And one of those narrow conditions, one of the least appreciated until recently, is something astronomers are now watching carefully on every exoplanet Webb studies. A condition so particular that it might be the single biggest reason our galaxy looks so empty. A condition hiding in how fast a planet spins. Here is a fact that took astronomers far too long to take seriously. If a planet orbits close enough to its star, the star's gravity eventually drags its rotation to a stop, or more precisely, locks it so that one side always faces the star, and the other side always faces away. The planet still orbits, but it no longer spins relative to its sun. Every day becomes eternal noon on one hemisphere, and eternal midnight on the other. Forever, that is called tidal locking. Our moon is tidally locked to Earth. It is why we always see the same face of it, and why the far side stayed a mystery until spacecraft finally flew around. What the moon is to Earth, a habitable zone planet is to a red dwarf star. Because red dwarfs are so dim, any world close enough to receive warm sunlight from them is also close enough to have its spin locked solid. And since 3/4 of every star in the galaxy is a red dwarf, the vast majority of habitable planets we will ever find are very likely tidally locked. Now think about what that does to a world. On the day side, the sun never moves. It hangs at the same spot in the sky for millions of years. That hemisphere is baked continuously, with no night to cool it. Temperatures soar. Oceans, if any existed, would evaporate into permanent cloud. Winds would rage across the surface like a hurricane that never stops. On the night side, the sun never rises, the temperature plummets, any atmosphere drifts over from the day, cools rapidly, and freezes solid on the surface as glaciers of nitrogen, methane, or whatever else the planet had. Oceans become ice so thick it never melts. No light, no warmth, no seasons. Between the two hemispheres runs a narrow ring, the terminator zone, where perpetual twilight reigns and temperatures might, in theory, allow liquid water. That thin band of dusk, a few hundred miles wide on a planet-sized world, is the only place where anything like life as we know it could exist. Could life evolve in a ribbon of dusk? Maybe. Microbes can survive almost anywhere. But complex life? A creature that needs stable climates to build nests, grow crops, cycle through generations without being baked or frozen? That is a brutal environment. And forget civilizations, forget cities, forget agriculture, forget anything that requires a planet's surface to be broadly habitable. A tidally locked world is, at best, a survival zone, not a thriving zone. And because tidal locking is the default for almost every habitable zone planet of almost every red dwarf star, which, again, is most of the galaxy's stars, it means the default habitable world out there may be a permanent, half-cooked, half-frozen nightmare. This solves a piece of the Fermi paradox without needing any filters or aliens or dark forests. Maybe most worlds have life only in a thin strip of twilight. Maybe most worlds can never grow something big enough to look up and wonder about other worlds. The galaxy is not full of potential Earths. It is full of bizarre half-lit planets where evolution, if it happens at all, is trapped in a dusk that never changes. There is a flicker of counter-argument. Some scientists have modeled atmospheres thick enough to redistribute heat around a tidally locked planet, smearing warmth across the night side. In those simulations, some tidally locked worlds might be more hospitable than the stark picture suggests, but those models require very specific atmospheres, thick enough to carry heat around the planet without blocking all the light, a narrow needle to thread. And again, Webb's early data is not kind. TRAPPIST, one's inner planets, all tidally locked, appear to have no such thick atmosphere. The dice are not rolling in our favor, so picture the galaxy again, and let your mind correct the picture. Not a scatter of Earth twins waiting to be met. A spray of baked half-worlds, frozen half-worlds, narrow rings of twilight where at best some microbe might cling. The silence begins to make sense. Not because life is rare, because most worlds, by the physics of their own suns, are never allowed to grow anything that would talk back. But even tidal locking is only one knife pointed at a living planet. There is a sharper one, and it does not sit beside the star. It erupts from it. You are standing on a warm, rocky world, a planet the size of Earth, orbiting a quiet red sun. You look up. The star hangs in the sky, dim and red, less than half as bright as our sun looks from home. It feels peaceful. Then, without warning, that star explodes. Not all of it, just a patch of its surface, maybe the size of a continent, unleashes a burst of energy so violent that it outshines the entire rest of the star for minutes. Ultraviolet light pours out in waves strong enough to burn exposed skin across an entire hemisphere. Behind the light, a cloud of charged particles races outward at millions of miles per hour, slamming into your planet's atmosphere like an invisible freight train. That is a stellar flare, and on red dwarf stars, it is not a rare event. It is Tuesday. Our sun throws a major flare every few years. Red dwarfs, because their magnetic fields tangle so aggressively, throw them constantly. Some of them fire off major flares, hundreds of times more energetic than anything our sun has produced in centuries. Astronomers have clocked super flares from nearby red dwarfs that would, if directed at Earth, strip away ozone, damage DNA across the planet's surface, and cook electronics into slag. Now realize the cruel geometry. Because red dwarfs are so dim, any planet in their habitable zone orbits dangerously close, much closer than Mercury hugs our Sunday. A flare that would be a minor inconvenience from safe distance becomes a planetary extinction event at point-blank range. Every flare does two things. First, it pounds the atmosphere's upper layers with ultraviolet and X-ray radiation, heating them until molecules break apart. Second, it hurls charged particles at the planet, where they collide with those broken molecules and knock pieces of them out into space. Do this once, and the planet barely notices. Do it 1,000 times a year for 1 billion years, and the atmosphere is gone, not partially, completely. Any ocean beneath it boils away into space. Any surface chemistry that might have birthed life is sterilized. This is almost certainly what happened to Mars. It orbits a calm star, but it lost its magnetic field early on and had no shield against the ordinary solar wind. Over billions of years, its atmosphere bled away until only a thin ghost remained. The same process, cranked up by a factor of 100, is what likely happens to every planet close to a flaring red dwarf. Webb has been quietly confirming this story. TRAPPIST, one's atmospheres or their absence are consistent with flare erosion. Other cool star planets Webb has examined show thin, battered skies. It is becoming a pattern. Red dwarf worlds are geological corpses, wrapped in whatever gas managed to survive the onslaught. There is a single defense a planet can mount: a strong internal magnetic field generated by a molten, churning core. Earth has one. It deflects the solar wind and keeps our atmosphere largely intact. Without it, we would be Mars. But magnetic fields are not easy to get. They require a planet with a liquid metal core, spinning fast enough to stir it, with enough radioactive heat to keep it molten over billions of years. Too small a planet, and the core cools too fast. Too old a planet, and the field fades. On a tidally locked world, which most red dwarf planets are, the slow rotation may even prevent a strong field from forming in the first place. So here is the running count of bad news for the galaxy's most common planets. They orbit flare-spitting stars. They are usually tidally locked. They probably have weak magnetic fields. Any atmosphere they start with gets stripped away within geologic blinks. Any ocean that might have hosted life gets hauled off into space. The universe is not failing to produce habitable planets. It is producing them and then murdering them. And even on the lucky worlds that escape the flames, yet another invisible problem waits one written into the very air itself. Take a deep breath. The air in your lungs is about 21% oxygen. That seems ordinary. It is anything but. Oxygen is one of the most reactive gases in existence. It grabs onto almost anything it touches. It rusts iron, it burns wood, it corrodes metal. In any natural setting, free oxygen should disappear almost immediately, soaked up by rocks and reactions in the crust. A planet's atmosphere should not have oxygen sitting around, and yet ours is full of it. That is because Earth's atmosphere is not in chemical equilibrium. It is being actively pumped every single second by living things. Plants and algae and cyanobacteria split water and release oxygen faster than rocks can absorb it. Cut the life, and within a few million years, all that oxygen would vanish. Our blue sky would turn into something more like Mars or Venus, dull, unreactive, dead. This is why oxygen has always been one of the holy grails of biosignature hunting. If you see abundant free oxygen in a distant planet's atmosphere, alongside a reducing gas like methane, something has to be making it. And the simplest something, by far, is life. But here is where the story gets dark for Fermi's paradox. Earth did not always have breathable air. For more than 2 billion years, half the age of our planet, the atmosphere contained almost no free oxygen. The oceans were full of dissolved iron, and microbes existed, but they ran on chemistry that did not release oxygen. Then, around 2.5 billion years ago, a new kind of microbe evolved: cyanobacteria. These tiny creatures cracked a trick that no one had ever cracked before. They used sunlight to split water molecules, pulling hydrogen off for fuel and spitting out the leftover oxygen as waste. For hundreds of millions of years, that oxygen had nowhere to go. It rusted the iron in the oceans, falling out as red sediment. When the oceans were finally saturated with rust, the oxygen started leaking into the air. Slowly, over hundreds of millions of years more, the atmosphere shifted. Oxygen rose. Most existing life, which had evolved in an oxygen-free world, was poisoned by it. We call this the Great Oxygenation Event, and for most of Earth's early biosphere, it was the worst catastrophe that had ever happened. Out of that wreckage, oxygen-breathing life evolved, and only then, 1.5 billion years later, did the first complex multicellular animals appear. No oxygen, no animals, no animals, no intelligence. No intelligence, no radio signals. Think about what that means for the galaxy. Finding a world with life is one thing. Finding a world where life has learned, by accident and evolution, to pump reactive gases into its own atmosphere for more than 2 billion years, long enough for complex biology to evolve, is something much rarer. A planet could host happy slime for billions of years and never take the step our cyanobacteria took. It would be alive, but forever invisible. No oxygen in its sky. No obvious chemical imbalance to give it away. Webb can detect oxygen, in theory. But the planets it is examining are mostly super-Earths and sub-Neptunes orbiting red dwarfs. On those worlds, oxygen is tricky. It can actually be produced without life, through ultraviolet light cracking water molecules apart and letting the light hydrogen escape to space. False positives loom. This is why Sarah Seeger and other astrobiologists have emphasized that there is no silver bullet biosignature. Oxygen alone is not enough. Methane alone is not enough. DMS alone is not enough. What you want is a combination oxygen and methane in the same sky, or DMS, in the wrong kind of atmosphere, or water vapor mixing with reactive chemistry that shouldn't coexist. Anything that screams of an imbalance being held up by an invisible hand, these chemical imbalances are the true fingerprints of life. They are hard to fake. They are harder still to detect at interstellar distances. And they teach us another piece of the Fermi answer. The galaxy may be full of quiet, living worlds whose atmospheres sit in sleepy equilibrium, alive, but unreadable. Only the rare, overachieving planet like Earth, where life went berserk and reshaped the entire atmosphere, would be visible as living from light years away. But even that is only one filter, because even a living, breathing planet can still be a dead end if its geology refuses to cooperate. Earth's surface is not solid. It is broken into enormous pieces called tectonic plates, each of them thousands of miles across, drifting on the hot plastic rock of the mantle below. Some of them crash together and build mountain ranges. Others pull apart and create oceans. Some slide past each other, grinding out earthquakes and volcanoes. Over hundreds of millions of years, entire continents migrate across the globe. For a long time, plate tectonics was thought of as an interesting feature of our planet. Pretty, violent, something that made geography strange. It turns out to be something much more important. It might be a requirement for complex life to exist at all. Here is why. Life depends on a stable climate, not unchanging, but roughly stable across millions of years. Carbon dioxide in the atmosphere is one of the main thermostats. Too much of it, and the planet overheats, the way Venus did. Too little, and the planet freezes into a global snowball, the way Earth nearly did more than once. To stay in the narrow Goldilocks band where liquid water can exist, a planet needs a way to constantly regulate how much carbon is in its sky. Plate tectonics does exactly that. When the atmosphere heats up, rain falls harder, weathering rocks more aggressively and locking carbon dioxide into the stone as carbonate minerals. Those minerals wash into the ocean, sink to the seafloor, and eventually get pulled down into the mantle at subduction zones where one tectonic plate dives beneath another. Deep inside the Earth, the carbon gets cooked out of the rocks and eventually belches back into the atmosphere through volcanoes. On, off, on, off. A self-correcting thermostat on a million-year cycle. Without plate tectonics, there is no such cycle. Carbon accumulates or disappears with nothing to balance it. Climate runs away. Venus, Earth's twin in size and composition, does not have plate tectonics. Its crust is a single rigid shell, its carbon dioxide piled up in its atmosphere with nowhere to go. The result is a surface temperature hot enough to melt lead and an atmosphere dense enough to crush a submarine. Mars, smaller and colder, also lacks active tectonics, and its atmosphere has simply bled away. Earth is the only rocky world in our solar system where plates still move. Whether this is a coincidence or a deep pattern, we do not yet know. What we do know is that plate tectonics requires very specific conditions. The planet has to be big enough to hold internal heat for billions of years, but not so big that the crust becomes too heavy and stiff to break. It has to have the right ratio of water and rock, because water lubricates the plates and lets them slide. It has to have a molten core, a convecting mantle, and probably the right combination of minerals in its crust. Each of these requirements is common in isolation. Stacking them all on the same planet is where things get rare. Webb cannot yet directly detect plate tectonics on exoplanets, but it can measure other things that hint at whether a world is geologically alive: the chemistry of its atmosphere, the presence or absence of specific volcanic gases, the rough temperature balance between day and night. Early results are quietly suggesting that many super-Earths out there do not have the right combination of conditions for plate tectonics at all. Some may have crusts too thick to break. Others may have lost their water and their lubrication. Others still may have simply cooled too fast. Stack this against everything else: red dwarf flares, tidal locking, oxygen traps. Now add, even on the worlds that dodge all those bullets, you still have to roll the dice on having a crust that recycles itself to keep the climate stable. It is starting to feel like Earth is not just one lucky planet. It is a planet that won a series of unlikely lotteries in a row. And there is one more of those lotteries waiting, and it is the one almost nobody thinks about when they imagine habitable worlds. The one that hangs in our sky every night. Go outside on a clear night and look up at the moon. Almost certainly, you have seen it 1,000 times. It is so familiar that it feels like a permanent backdrop, nothing special. But the moon is strange, astonishingly, unreasonably strange, and its strangeness may be a huge reason you exist to look up at it. Start with the size. Our moon is enormous compared to Earth. Its diameter is more than a quarter of Earth's own. In the entire solar system, no other rocky planet has a moon anything close to that ratio. Mars has 2 tiny captured asteroids. Venus has nothing. Mercury has nothing. The gas giants have moons, some of them large in absolute terms, but none comparable in proportion to our pairing with the moon. That ratio is so unusual that planetary scientists believe it was not formed by any normal process. The leading theory is that, roughly 4.5 billion years ago, a planet the size of Mars slammed into the young Earth at a glancing angle. The collision vaporized huge chunks of both worlds. Some of the debris fell back to form the molten Earth we know. The rest coalesced in orbit and cooled into the moon. 2 worlds born from one catastrophic crash. That explains the moon's size. Here is why that size matters. Earth is tilted on its axis by about 23 degrees. That tilt gives us seasons. Summer and winter flip as our hemispheres lean toward and away from the Sunday. This tilt has stayed remarkably stable over billions of years, wobbling by only a degree or 2. That stability is why climates on Earth have been predictable enough for complex life to evolve. Without the moon, that tilt would wander wildly. Computer simulations of a moonless Earth show axial tilts that could swing from nearly 0 degrees, meaning no seasons at all, just a permanent mild climate at the equator, and frozen poles to as much as 85 degrees, where one hemisphere would face the sun for months at a time, and then plunge into months of darkness. Climates would lurch between extremes on timescales of tens or hundreds of thousands of years. Complex life does not evolve well under those conditions. Evolution needs stable pressure, slow change, the room to develop eyes, brains, reproductive strategies that make sense across generations. A planet whose climate randomly cooks or freezes every few tens of thousands of years is a planet where life stays simple, survives in pockets, or dies back to slime. The moon prevents all of that. Its gravity holds Earth's tilt steady, like a finger pressed on a spinning top. Without it, we would probably still have oceans and air, but the planet would be a different, more chaotic place. Whether humans could have evolved at all is an open question. Now, look outward at exoplanets. How many are likely to have giant moons like ours? Almost none. Giant impact moon formation is a freak event. It requires a specific kind of collision, at a specific kind of angle, at a specific point in a planet's early history. Most rocky planets have either no large moon or, at best, a captured asteroid that provides no stabilizing effect. This is quietly another rare Earth factor. Even if a planet has the right size, the right star, the right atmosphere, the right oceans, the right tectonics, if it does not also have a big stabilizing moon, its climate may be too chaotic to grow complex life on long timescales. And here is an eerie thing to sit with. The moon is slowly drifting away from Earth, about 1.5 inches every year. In a few billion years, it will be too far away to stabilize our tilt. Earth's climate will become wobbly. Whatever life exists then will face a kind of chaos our ancestors never had to endure. We live in a narrow window, on a pair of worlds that were born together in fire, and we hardly ever notice it. Somewhere out there, other worlds without such a partner may have everything else and still never quite make it. But even a well-moonlit planet has one more enemy that can ruin everything. An enemy that comes from the depths of space, hurtling at the planet with the force of 1,000 nuclear bombs. On the night of July 16, 1994, astronomers across the world pointed their telescopes at Jupiter and watched something unbelievable happen. A comet called Shoemaker-Levy 9, which had been torn apart by Jupiter's gravity 2 years earlier into 21 chunks, slammed into the giant planet's atmosphere, one piece at a time. Each impact released the energy of millions of nuclear weapons. Dark blotches appeared on Jupiter's cloud tops, some of them larger than the entire Earth. Astronomers watched the scars linger for months. It was the first time in history that humans had actually witnessed a collision between two bodies in our solar system, and every astronomer who watched thought the same thing: that could have been us. Jupiter is our bodyguard. Its enormous gravity, 300 times Earth's, acts like a vacuum cleaner in the outer solar system. Comets and asteroids that wander too close are either flung away entirely or dragged down into the giant's atmosphere, destroyed before they ever threaten the inner worlds. Over billions of years, Jupiter has almost certainly saved Earth from countless impacts that would have reset our evolution or ended it. The story is a bit more complicated than that. Recent computer simulations suggest Jupiter is not a perfect shield. In some scenarios, its gravity can actually fling objects inward as often as it absorbs them. But the dominant picture is still one of protection. On the timescales that matter for evolution, Jupiter has made Earth a calmer neighborhood than it would otherwise have been. Earth still takes hits. 66 million years ago, a 10-kilometer asteroid smashed into the Yucatan Peninsula, ending the age of dinosaurs and roughly 3/4 of all species on the planet. But those catastrophic impacts are spaced tens of millions of years apart. Without Jupiter, they could come every few 100,000. No complex life could survive the steady beating. Now, look at other star systems. Most of them, as far as we can tell, do not have a Jupiter in the right orbit. Some have gas giants. Yes, but in the wrong places. Many systems have what astronomers call hot Jupiters, giant planets that migrated inward and now hug their stars at closer than Mercury distances. In those systems, any Earth-like world that tried to form in the habitable zone would have been flung out or destroyed during the migration. Other systems have giant planets on wildly eccentric orbits that would have scoured the inner region of any small rocky worlds long ago. A well-behaved Jupiter on a well-behaved orbit, like our own, seems to be another unusual arrangement. Not impossible, just not the default. Webb is beginning to survey the architectures of distant planetary systems, and the diversity is staggering. Some systems are packed with small planets crammed close to their stars, with no outer giants at all. Others are dominated by hot Jupiters or elongated giants. Only a minority resemble ours, with small rocky worlds inside and stable gas giants outside. If a Jupiter-like shield is a requirement for long-term evolutionary stability, then once again, the pool of planets where complex life could evolve shrinks. Stack the filters: sun-like star, galactic habitable zone, right size, plate tectonics, large stabilizing moon, Jupiter-shaped protector in the outer system, magnetic field, thick atmosphere, a big ocean but also continents, oxygen-producing life that somehow survived its own poisoning, and time billions of years of relative peace for complexity to grow. Each condition is reachable. Stack enough of them, and the number of worlds left in the galaxy that could plausibly birth an intelligent species starts to look terrifyingly small. Maybe dozens, maybe one. Us? And that is if we assume other civilizations, once they exist, broadcast loudly and confidently into the void. But a growing school of thought suggests exactly the opposite, that any civilization smart enough to last more than a few hundred years has learned to stay very, very quiet, because the universe might not be empty at all. It might be a hunting ground. In 2008, a Chinese science fiction writer named Liu Cixin published a book called The Dark Forest. Inside it, he proposed one of the most chilling solutions to the Fermi paradox ever written. Scientists have argued about it ever since, because while it is framed as fiction, its logic is terrifyingly airtight. The argument goes like this. Start with two assumptions. First, every civilization wants to survive. Second, in the vastness of space, you can never really know another civilization's intentions. Given those two facts, every civilization faces an impossible question when they detect another one. Are those aliens friendly? Hostile? Are they rivals for resources? Could they destroy us? And crucially, could they destroy us before we could destroy them? You cannot know. Distances are too great. By the time you receive a signal from another civilization, it was sent hundreds or thousands of years ago. By the time you reply, another few hundred years pass. You might be negotiating with ghosts. You might be negotiating with an empire that has grown during those centuries, strong enough to annihilate you. In that situation, Liu argued, there is only one rational first move: strike first. Because if you reveal yourself and they are hostile, you are dead. If you hide and they find you anyway, you may still die. But if you strike them while they are young and weak, you remove the threat forever. And critically, they must reason the same way, which means they will strike you if they ever learn you exist. The only safe move, under these assumptions, is to never, ever be seen. Hence the name. The universe is a dark forest. Every civilization in it is a hunter, creeping through the trees, trying to stay absolutely silent. The moment anyone makes a noise, a radio broadcast, a directed laser, a power signature from a Dyson swarm, every other hunter instantly knows their location, and the nearest one with the means to strike will do so, not because they are cruel, because they cannot afford not to. In such a universe, the galaxy could be teeming with life, and we would never know it. Every civilization that survived long enough to become advanced is the civilization that learned to shut up. The ones that did not survive long enough are the ones that broadcasted loudly and were silenced. We, by this logic, are a baby in the dark screaming at the top of its lungs. Our radio broadcasts have been leaking into space for more than a century. A sphere of our earliest transmissions now stretches out more than 100 light-years in every direction from Earth, carrying our sitcoms and our speeches and our declarations of existence to any ear that might be listening. Any sufficiently advanced civilization within that sphere could already know we are here. If the dark forest theory is correct, we may have already made a fatal mistake. The counter-argument is that the theory rests on some hard assumptions, that distances really are insurmountable to meaningful diplomacy, that every civilization thinks in terms of self-preservation at all costs, that there is no path to cooperation, trust, or some universal ethical framework that transcends fear. These assumptions can be challenged. Life on Earth often cooperates more than it competes. Maybe interstellar civilizations do too. But here is the unsettling part. Even if 99 out of 100 civilizations are peaceful, you only need one predator for the dark forest logic to apply. Once predators exist, peaceful civilizations that broadcast freely get eaten. Peaceful civilizations that learn to stay quiet survive. Over millions of years, the galaxy filters itself into hunters and hiders, and if that filtering has already happened, the silence we hear is not empty. It is deliberate. It is the sound of millions of civilizations holding their breath. Some scientists take this theory seriously enough that they actively argue against sending deliberate messages into space. They call the practice meti-messaging, extraterrestrial intelligence, and they consider it a kind of planetary suicide. Stephen Hawking, in his final years, warned that advertising our presence could be the worst mistake humanity ever made. He may have been paranoid, or he may have been right. We have no way to know until the answer arrives by a signal we welcome, or by something else. Either way, the question of whether to speak or stay silent is now one of the most serious debates in the entire search for alien life. The year is 1974. A huge radio dish in Puerto Rico called Arecibo, the largest telescope on Earth at the time, is being upgraded. To celebrate, the astronomers running it decide to do something that has never been done before. They will send a message to the stars. The target is a cluster of stars called Messier 13, 25,000 light-years away. The message is simple. It is a string of numbers, a picture of a stick figure human, a sketch of our solar system, and the basic structure of DNA. A postcard, encoded in radio waves, beamed at a cluster in the constellation Hercules. The message will arrive at Messier 13 in about 25,000 years. By then, the cluster itself will have moved significantly, and the target may no longer be where the message is aimed. But the point was symbolic. Humanity had shouted into the dark for the first time. Since then, several more deliberate messages have been sent, most of them aimed at nearer stars, a handful of them aimed at worlds we now know have planets. In a few decades, to a few centuries, our invitations will begin arriving at their destinations, and some scientists think that this is the most reckless thing our species has ever done. The argument is the dark forest made practical. Until the invention of radio, Earth was a quiet planet. Its atmosphere had oxygen, which advertised life. But you needed a very powerful telescope pointed exactly at us, at exactly the right time to notice. That meant we were essentially invisible to anyone without a reason to look. The invention of radio changed that. Every broadcast we make, every television signal, every military radar, every satellite uplink leaks into space at the speed of light. A sphere of that leakage now surrounds our planet, more than 100 light-years across. Any civilization inside that sphere, with a decent radio telescope, could detect our presence and roughly work out our location. That leakage is probably too faint to pick up from far away. But deliberate messages, like Arecibo, are different. They are narrow, focused beams of high-powered radio. They can be detected by a modest telescope from thousands of light-years away. They scream, "Here we are, here we are, here we are," to anyone who happens to be listening in that direction. Critics of this practice argue that we are making a decision that could affect all of humanity for all time, with no mandate, no oversight, and no global agreement. A handful of astronomers, in a handful of rooms, choose to send signals on behalf of the entire species. Some of these critics, including several serious scientists, have demanded a moratorium on deliberate transmissions until we better understand the risks. The defenders counter that it is too late. Our inadvertent leakage has already given us away. Any civilization capable of crossing interstellar distances to harm us could detect us regardless of whether we send deliberate messages or not. More broadcasting, they argue, changes nothing. And besides, if friendly civilizations exist, deliberately waving at them is how we make contact. Both sides have a point. Our leakage probably is detectable by a sufficiently advanced observer, but it fades with distance much more quickly than a focused, high-powered beam. Deliberate messages make us stand out dramatically on the galactic radio landscape. Whether that is suicide or hello is exactly the question we cannot yet answer. There is a darker variant of this debate. Some scientists worry that Webb's own observations could betray us. If we confirm life on an exoplanet and broadcast the news, we are telling the universe where to find a living world. If some other civilization is watching the electromagnetic spectrum for such announcements, they now know both where Earth is and where we are interested in going. It is not a direct invitation to visit, but it is a bright marker on a cosmic map. This is not idle paranoia. Every civilization in history has had to reckon with the question of what to do when a more powerful stranger arrives. The answer has rarely been good for the less powerful side. We have been loud for only a century. We will continue to be louder, whether that noise attracts friends, attracts enemies, or attracts nothing at all may be the most important unresolved question about our own future. And if it attracts anything, it may attract something far stranger than the aliens of movies. Something that does not fit in a ship or a species at all. In 1973, an MIT radio astronomer named John Ball proposed a different answer to Fermi's question, and it is one of the most unsettling precisely because it cannot be disproved. What if the aliens know we exist and are deliberately leaving us alone? This is the zoo hypothesis. The idea is that the galaxy may contain many advanced civilizations. Those civilizations may be watching Earth the way a naturalist watches a nature preserve. They have rules about not interfering with pre-contact species. They allow us to develop undisturbed because either ethics or curiosity dictates it, or because they are afraid of corrupting our natural path. You could call it the Prime Directive if you are a Star Trek fan. Scientists call it the zoo hypothesis because we are the animals in the enclosure, unaware that we are being observed. The idea sounds fantastical, but it solves the Fermi paradox elegantly. It explains why we see no activity without requiring that civilizations be absent. It explains why we hear no signals without requiring that everyone is hiding in terror. The aliens are there. They simply choose not to intrude. The weakness of the zoo hypothesis is that it requires extraordinary coordination. Every advanced civilization in the galaxy would have to agree to leave us alone, all of them. No cheaters. No scientists who break the rules and poke us anyway. No rogue factions who decide they want to say hello or take a sample. For hundreds of thousands of years, perhaps millions, the quarantine has held. That kind of consensus is hard to imagine. Human civilizations cannot even agree on trade rules for a decade, expecting millions of years of perfect cooperation among alien species, possibly with wildly different psychologies, seems like a stretch. Defenders of the hypothesis argue that the coordination problem is only hard if civilizations are comparable in power. If there is a galactic senior civilization that enforces the rules on the others, then coordination becomes possible. The oldest, most advanced species in the Milky Way, whoever they are, could quietly police the younger ones, preventing premature contact with species like us. This is an old idea dressed up in new clothes. It sounds like the watchers or observers from countless science fiction stories, but it has one feature that is scientifically interesting. It is essentially unfalsifiable from inside the zoo. If the observers are clever enough, they can make their own surveillance invisible to us. Any evidence we might find of alien activity could be, by design, withheld, which means the hypothesis cannot be tested. We cannot prove we are in a zoo. We cannot prove we are not. Some scientists find this philosophically unsatisfying. A good theory should make predictions we can check. The zoo hypothesis makes none. It is more of a speculation than a scientific proposal. Still, it lingers because it captures something true. If advanced civilizations exist and can reach us, their absence from our skies requires an explanation. Either they cannot come, or they will not come. The zoo hypothesis bets on the second option, and it elevates the reason to something morally complex. Maybe they respect our autonomy. Maybe they pity us. Maybe they simply find us uninteresting. Maybe they are waiting for us to prove ourselves worthy of contact. Any of these, however speculative, is at least consistent with the data, and the data, as of 2026, is that we see nothing, hear nothing, and find nothing. There is one variant of this hypothesis that disturbs even the people who propose it. What if the observers are not benign? What if the silence is not protection, but examination, and the decision about what to do with us is still being made? Every century that passes, as we develop further, as we begin to leave our cradle and reach toward the stars, we move closer to whatever judgment is awaiting us. Nobody takes this seriously as science, but nobody can rule it out either. Which brings us to a different kind of unfalsifiable explanation, one that dissolves not only the Fermi paradox but the entire universe along with it. In 2003, a philosopher at Oxford named Nick Bostrom published a paper that did something unusual. It took an idea that had previously lived only in science fiction and turned it into a genuine academic argument. He called it the simulation hypothesis. The paper presented a simple chain of reasoning that a lot of serious scientists have been unable to shake off. Bostrom's argument works in 3 steps. First, assume that a sufficiently advanced civilization could, in principle, run computer simulations detailed enough to include conscious beings inside them. Second, assume that such civilizations, if they exist, would probably run many such simulations, perhaps for research, entertainment, or ancestor study. Third, realize that if many simulated civilizations exist for every real one, then statistically, most conscious beings are simulated, including, probably, us. This argument is not proof. It depends on its assumptions, and any one of them can be challenged. But it is remarkably difficult to dismiss entirely. And it offers, almost as a side effect, a complete solution to the Fermi paradox. If we are in a simulation, the universe we perceive is not necessarily the complete universe. Our galaxy, our cosmic microwave background, our distant stars, these might all be rendered on demand, generated when we look at them and ignored when we are not. The other civilizations we expect to find may not need to exist because they are not part of the simulation story. The simulation is about us, the rest is decoration. In this view, the silence is not a mystery, it is a rendering choice. The simulators did not include other species because other species were not part of what they wanted to study. As weird as this sounds, it has gained traction among some serious scientists, including physicists and computer scientists. They point out that modern video games already simulate large worlds populated with background characters, most of whom exist only as code that runs when the player is nearby. If we extrapolate that trend by a few centuries of computing power, simulations of entire universes with conscious inhabitants start to look plausible. The strongest objection is that there is no known physical mechanism by which a simulation of our observed complexity could be built, even in principle, without being at least as complex as the universe itself. Running a universe takes universe-scale resources. This objection is not decisive. A simulator civilization might have access to resources we cannot imagine, but it is a real obstacle. More importantly, from a scientific perspective, the simulation hypothesis is almost impossible to test. If the simulation is well designed, we cannot tell we are in it. Any glitches that might reveal it would, presumably, be patched out before we noticed. Any experiment we could run would be captured by the simulation itself. So unless the simulators are careless, we will never know. This leaves the hypothesis in an awkward place. It may be true, it may be completely wrong. It offers a complete answer to the Fermi paradox that cannot be verified or falsified. Most scientists, when pressed, treat it the way they treat other philosophical speculations. Interesting, worth considering, not something to plan around. We still have to act as if the universe is real, because that is the only universe we have access to. But for what it is worth, the Fermi paradox is one of the reasons the simulation hypothesis keeps getting mentioned in serious rooms. When a problem this big has no satisfying answer within the standard model, some thinkers are tempted to question whether the standard model is itself correct. The silence may be telling us something about the nature of reality, not about the nature of biology. Or, more soberly, the silence may have a much more conventional explanation, one that does not require rewriting physics or philosophy. An explanation rooted in very old machines, built by very old civilizations, that continue doing what they were told to do long after their creators are gone. In 1963, science fiction writer Fred Saberhagen published the first of what would become a long series of stories about killer machines. He called them Berserkers. They were ancient self-replicating war machines, built by a long-dead civilization as a weapon against another long-dead civilization, and now left wandering the galaxy, hunting and destroying any life they could find. They had no off switch. Their makers were gone. The machines simply continued. It is fiction. But astronomers have found themselves forced to take the idea seriously because it solves the Fermi paradox in a brutally efficient way. Consider what happens if, at some point in the galaxy's history, even a single civilization builds self-replicating probes designed to attack life. Those probes spread from star to star, building copies of themselves at each stop. Over 10 million years, they reach every habitable planet in the galaxy. When they find a biosphere or a civilization, they destroy it. Then they move on. After a few passes, the galaxy is effectively sterilized, not dead. Life keeps emerging. But whenever a civilization rises to a detectable level of technology radio, megastructures, visible changes to their atmosphere, a Berserker probe, or a swarm of them, eventually arrives and wipes them out. Nothing ever gets big enough or old enough to be seen. This works without requiring any living enemies. The original civilization that built the machines may be long gone. The machines outlive them, dumb and persistent, following their original orders across geologic time. The Berserker hypothesis is a variant of the dark forest, but it is more final. In the dark forest, civilizations survive by hiding. With Berserkers, no amount of hiding is enough, because the machines sweep every star system regardless of whether they detect anyone. Their strategy is prevention. Kill potential competitors before they can ever rise. For this to explain Fermi's silence, we only need one ancient civilization to have built one Berserker fleet, at least once, anywhere in the Milky Way's 10 billion year history. A single successful launch, and the rest of the galaxy is trapped under the probe's shadow forever. Some physicists have argued this is the most parsimonious explanation for the silence we observe. It requires only one ancient enemy. It does not require perfect coordination among civilizations, as the zoo hypothesis does. It does not require every civilization to destroy itself, as some versions of the Great Filter do. It just requires one. And once you have one, you have an empty galaxy forever. There is some cold comfort in the fact that we have not, so far, been destroyed. Our radio leakage has been crossing space for more than a century. Our atmosphere has advertised oxygen-producing life for more than 2 billion years. If Berserker probes were truly everywhere, shouldn't they have noticed us by now? Perhaps. Or perhaps the nearest one has not yet arrived. Space is enormous. Even a probe that hops from star to star at a meaningful fraction of light speed takes time to cross the galaxy. If we are in a corner that has not been visited recently, if the sweep pattern is patchy, we might have time yet. Or, more hopefully, the entire scenario might be wrong. No civilization may have ever built such machines. The technology may be harder than it seems. The motivation may be rarer than we imagine. Evolution, even among thinking species, may produce fewer genocides than the worst-case scenario assumes. We cannot tell. The Berserker hypothesis is, like the zoo, essentially untestable from our current position. We will either meet the probes one day, or we will not. If we do, we probably will not live long enough to warn anyone. But there is an entirely different kind of explanation for the Fermi silence that has nothing to do with violence at all. An explanation in which every advanced civilization simply leaves, not by dying, not by hiding, not by being hunted, but by transcending physical space itself. In 2011, a futurist named John Smart proposed a strange idea. What if the reason we do not see advanced civilizations is not because they are dead or hiding, but because they have, in some sense, left the ordinary physical universe? He called it the transcension hypothesis. The argument goes like this. As a civilization advances, its computation gets denser, its physical footprint gets smaller, not larger. Our own history already hints at this pattern. A computer that filled a room in the 1960s now fits in a watch. A library that once required a building now fits on a chip. Technology miniaturizes. Extrapolate this trend into the far future. A civilization sufficiently advanced might compress its infrastructure, its consciousness, and its entire way of life into extraordinarily small and dense structures. Not bigger Dyson swarms. Smaller, more efficient, operating at temperatures and energies we cannot easily detect. At some point, Smart argued, civilizations might find that it is more efficient and more interesting to inhabit inner space than to expand into outer space. Instead of colonizing stars, they colonize the interior of black holes, the quantum foam, the computational potential of exotic matter. They disappear from view, not because they are gone, but because they have gone somewhere we do not know how to look. This solves the Fermi paradox without any violence or extinction. It simply says that sufficiently advanced civilizations stop caring about traveling between stars. They have better things to do. The argument draws on real trends. Miniaturization is real. Computational density is rising. The energy efficiency of computation is improving by orders of magnitude every few decades. If any of those trends continue far enough, eventually you get civilizations that use vanishingly small amounts of matter and energy to do vanishingly huge amounts of thinking. From the outside, such a civilization would be nearly invisible. It would not broadcast. It would not build Dyson spheres, because those waste space. It would not launch probes, because physical exploration is boring compared to whatever they are doing internally. It might even actively shield itself from the outside universe, either to protect its delicate computations, or because the outside no longer matters to it. If most civilizations follow this path, then the Fermi silence is expected. We do not see them because they are operating in a regime of physics and engineering that we cannot yet detect, doing things we cannot yet imagine, in places we do not yet know how to search. The weakness of this hypothesis is that it requires every civilization to follow roughly the same path. If even one civilization out of a million decided to keep expanding physically for fun, out of stubbornness, out of genuine desire to explore, we should see that civilization, one species, in 10 billion years of galactic history, with a stubborn streak and a tolerance for long travel times, could fill the galaxy with visible activity. Transcension only works as a complete solution if it is not optional, if the pull toward inner space is so strong that every advanced civilization eventually gives in. That is a big claim. It requires assumptions about the psychology and motivations of species we have never met. Still, the hypothesis has a certain elegance. It takes trends we already see in our own civilization and extrapolates them. It does not require enemies, cataclysms, or conspiracies. It simply says that growing up for a civilization means outgrowing the stars themselves. If that is true, our search for aliens may be fundamentally misdirected. We are looking for bigger, brighter, louder civilizations. We might need to look for smaller, quieter, darker ones. Or not look for them at all, because once they have transcended, they may have left no trace we know how to read. There is a final possibility that deserves consideration, one that requires neither death, nor hiding, nor departure. A possibility that the galaxy really is full of civilizations, they just never all exist at the same time. Picture a field at dusk. Fireflies begin to blink. Here, there, a flash of green, then dark. A new flash somewhere else, then dark again. If you stand in the field for a minute, you see many fireflies. But if you could only see an instant, one single frozen fraction of a second, you might see only one, or none. Our galaxy may work the same way. The Milky Way is roughly 10 billion years old in its life-friendly form. In all that time, civilizations may have risen and fallen across its disk, but none of them have lasted more than a few tens of thousands of years. A civilization that lives for, say, 50,000 years is a long-lived one by the standards of human history. But on a galactic timescale, 50,000 years is a wink. Now, imagine that, on average, one civilization arises in the galaxy every 100 million years. In 10 billion years, that is 100 civilizations. That sounds like a lot, but each one lives, say, 50,000 years. So at any given moment, the fraction of the galaxy's history occupied by an active civilization is 50,000 divided by 100 million, a half thousandth, 0.05%. Most of the time, there are none. Occasionally, by chance, two might exist simultaneously, but probably on opposite sides of the galaxy, unable to reach each other across tens of thousands of light years. This is the timing problem. It does not require any mysterious filter or hidden hunter. It just requires that civilizations do not last very long relative to the timescales on which contact is possible. Given the distances involved, even civilizations that existed simultaneously in the galaxy could easily miss each other simply because their signals never caught up before one side collapsed. Earth has had radio for about 130 years. If we collapse in the next few centuries, our total signaling window will have been less than 1,000 years. A civilization 5,000 light years away, with a similar window but offset in time by a few thousand years, would never detect us, and we would never detect them. We would be a pair of fireflies that blinked on opposite sides of the field, a minute apart, and never saw each other. This is a surprisingly popular hypothesis among professional astronomers because it requires no exotic assumptions. Civilizations do not need to destroy themselves intentionally. They do not need to be hunted, they simply need to be transient to rise, flourish, and eventually fade, whether through cultural collapse, natural disasters, loss of interest, or simply statistical mediocrity. Our own civilization provides a hint. We have existed for a few 100,000 years, and we have had technology capable of interstellar signaling for only the last century. Whether we will last another century, another millennium, or another million years is genuinely unknown. Our culture's own sustainability is not guaranteed. The odds that we happen to exist simultaneously with another civilization within signaling distance are slim, especially if other civilizations have the same kind of short windows. This also explains, gently, why SETI has heard so little. Even if the galaxy is full of civilizations across its history, most of them are dead by the time their light reaches us. and most of the ones still alive are too far away or too quiet to detect. We might be in a brief moment of galactic loneliness that is entirely typical. There is a small, hopeful twist. If we can stretch our own lifespan, if we can make our civilization last not thousands but millions of years, then the odds of contact rise dramatically. A long-lived civilization has more chances to detect others and more chances to be detected. Longevity, in this scenario, is not just about our own survival. It is about how likely we are to ever meet another mind. For the first time in history, we have tools powerful enough to possibly spot the faint chemical signature of another world's biosphere, even if its makers are long dead or not yet born. Webb is already doing this, and a much more powerful successor is being designed right now that will do it better. Much better. Step back from the astronomy for a moment and imagine the day. An astronomer steps up to a podium. Cameras click. The screen behind her shows a spectrum, a jagged line of color absorptions, red and green and blue. She points at certain dips in the line. She explains that these dips represent specific molecules. She names them oxygen, methane, water, a biosignature gas, unlike any known non-biological process. She says the result has been confirmed, independently, by multiple teams, at 5 sigma confidence or better. The probability of coincidence is essentially 0. She says, calmly, that the best explanation for what has been observed is that the planet hosts life. That announcement has not happened, but when it does, and most astronomers now believe that in the next 10 to 20 years, nothing about human society will be the same afterward. It is hard to predict exactly what that day will feel like, because nothing in our history quite compares. The closest analogy might be the day in 1592 when Galileo first pointed his telescope at Jupiter and discovered 4 moons orbiting it. That discovery, a single night's observation, broke 1,000 years of belief that Earth was the center of everything. It triggered centuries of upheaval in religion, philosophy, and science. A confirmed biosignature on another world would do the same, but faster and to more people because we now have global communications. Here is what would probably happen in the first week. Stock markets would move sharply because anything involving space, biotech, and technology firms would become, overnight, vastly more interesting. Religious institutions would issue statements. Most of them would adapt quickly. Major faiths have actually thought seriously about this for decades, and several have concluded that alien life would not conflict with their theology. Others would struggle, and some denominations would fracture. Nations would scramble to claim leadership of the search. Space agencies would find themselves suddenly flooded with funding. New telescopes, new probes, new missions would be greenlit at speeds unthinkable in normal times. But the deeper effects would unfold more slowly, over years and decades. The first would be a quiet, widespread psychological shift. Polling in multiple countries has shown that for most people, the confirmation of microbial life elsewhere would not actually be that traumatic. Many people already assume aliens exist. The confirmation would feel more like a long-expected phone call than a shock. The shift would come in the background. Young people, hearing about the discovery in school, would grow up taking it for granted that life is not unique to Earth. Their worldview would quietly differ from every generation before them. Over 50 years, that difference would show up in philosophy, in art, in religion, in how we think about ourselves. For scientists, the effect would be even more dramatic. A confirmed biosignature would transform astrobiology from a speculative field into the central question of biology itself. Every aspect of life we had thought was universal, based on DNA, based on carbon, based on water, would suddenly have to be re-examined in light of what that other planet was doing. Did it use the same chemistry? Different chemistry? How different? The answers would reshape genetics, biochemistry, evolutionary theory, and our understanding of life's origins here on Earth. And there would be a longer, slower question sitting behind all of it. If simple life is now known to exist elsewhere, what about complex life? What about intelligent life? Every argument for the great filter would come back, sharper than ever. Is the filter behind us or ahead of us? That question would become the defining preoccupation of our century. because once we know slime is common, the silence gets louder, much louder. And Webb, as powerful as it is not enough to fully answer it. The next telescope is already being designed, a telescope so ambitious that it will make Webb look like a warm-up act, and it has one job, above all others. In 2021, before Webb had even launched, an advisory panel to the United States government, the ASTRO 2020 Decadal Survey, delivered its recommendations for what the next generation of astronomy should prioritize. At the top of the list was something audacious, a new space telescope, much bigger than Webb, designed from scratch for one central purpose: to find biosignatures on Earth-like planets around Sun-like stars. They called it the Habitable Worlds Observatory. It is still in early planning stages. Its launch target is somewhere in the 2040s. Its mirror will be bigger than Webb's. Its instruments will be engineered specifically to directly image exoplanets, not just sniff their atmospheres during transit, but actually block out their host stars and see the planets themselves as pale blue dots. This is a radically different capability. Webb can only study exoplanets indirectly by watching the tiny wobbles of starlight as a planet passes in front. That method works best for big, hot planets orbiting small, cool stars. It works poorly for small, rocky planets orbiting sun-like stars, which is exactly the category Earth falls into. To find an Earth twin, you need a different trick. The Habitable Worlds Observatory will use something called a coronagraph, a complex optical device that blocks the light of a star to incredible precision. With enough precision, you can see a planet 1/10 billionth as bright as its star, sitting just a fraction of an arc-second away from it. That is the kind of contrast you need to image an Earth-like planet directly. If it works, the observatory will be able to point at a nearby sun-like star, suppress its light, and see a true Earth twin as a single bright speck. Then it will analyze the light coming from that speck, its atmosphere, its oceans, if any, its continents, if any, even, with clever techniques, its seasons, its weather patterns, the faint greens and blues that would hint at photosynthesis. And it will look for biosignature gases directly: oxygen, methane, nitrous oxide, ozone, combinations that would reveal a living biosphere at work, even from tens of light years away. The observatory is designed to survey roughly 25 Earth-like planets within a few dozen light years of our Sunday. That sounds like a small number, but it is actually enormous. Right now, we do not have any confirmed Earth twins. We have super-Earths and sub-Neptunes and Hycean candidates, but no actual Earth-sized planet around a sun-like star that we can study in detail. The Habitable Worlds Observatory will give us 25 or more if the first results are encouraging. That is enough to answer one of the deepest questions of the Fermi paradox. Not, is the galaxy full of civilizations? We may never know that, but is Earth-like biology rare or common? If the observatory examines 25 Earth twins and finds 5 of them alive, we will know life is common. The great filter is almost certainly behind us. The universe is full of microbial worlds. If it examines 25 and finds 0, we will know something is wrong with the easy assumption that slime is everywhere. Either Earth is genuinely exceptional, or the filter is much harder than we thought. Either answer changes everything about our understanding of ourselves. The observatory is not cheap. Its estimated cost is well over $10 billion, on par with Webb itself. Its development is already beginning. Its science goals are clear. If funding holds, if the engineering works, it will launch in our lifetimes, and its first data will arrive in the late 2040s. There is a chance that Webb will confirm life first, before the new observatory even launches. There is also a chance that Webb's candidates will all turn out to be false alarms, and that the decisive answer will have to wait for the next telescope. Either way, the pace of discovery is accelerating. We are not going to be stuck with Fermi's question forever. The tools to answer it are being built right now, and the next 5 years, in particular, may be the most important in the entire history of the search. As of 2026, Webb has been operating for about 4 years. In that time, it has examined the atmospheres of dozens of exoplanets. Its most tantalizing target, K2-18b, has provided a contested biosignature signal. Its most disappointing results, TRAPPIST, one's inner planets, have shown no atmospheres at all. Its most surprising discoveries, Hycean planet candidates, strange chemistry in sub-Neptunes, have opened whole new categories of habitable worlds. And Webb is only getting started. Its mission has been extended through the early 2030s. In that time, it will examine many more exoplanets, follow up on promising biosignature candidates, and refine our understanding of atmospheres across every type of world. The K2-18b question, specifically, is scheduled for more observation time. The scientific community has made clear that resolving the DMS controversy, either confirming or rejecting the signal, is a top priority. Within 5 years, we should have a definitive answer on that single world. But Webb is not alone. Several other instruments are either recently online or coming online soon. The European Southern Observatory's extremely large telescope, a ground-based instrument with a mirror nearly 40 meters across, is scheduled to see first light late in this decade. Its sheer size will let it probe exoplanet atmospheres at resolutions Webb cannot match. Another project, the 30-meter telescope, is also being built, though politically fraught. Additional dedicated exoplanet missions, like the European Space Agency's Plato and NASA's upcoming Roman Space Telescope, will be surveying the sky for new habitable zone planets around sun-like stars. The combined power of all these instruments, working together, means that the next 5 to 10 years should see the number of studied exoplanet atmospheres jump from dozens to hundreds. Patterns will emerge. The outliers, the truly strange worlds, will stand out, and the list of the best candidates for hosting life will sharpen dramatically. This is unprecedented. Every previous generation of astronomers has had to argue about Fermi's paradox using very little direct evidence. Our generation is the first that will have real data, not about alien civilizations directly that may still take much longer, but about whether life itself is common or rare, about whether the great filter is behind us or ahead of us, about whether Earth is ordinary or exceptional. Here is the sharpest reason to pay attention. The odds are genuinely high that within the next decade, one of two things will happen. Either we will confirm a biosignature on an exoplanet, possibly K2-18b, possibly one we have not yet discovered, and the search for life will move from speculation to concrete investigation. That would be the discovery of the century. It would fundamentally alter humanity's understanding of itself. It would trigger massive investment in follow-up missions, probes, and eventually, maybe, plans to visit. Or, alternatively, we will fail to confirm any biosignatures despite looking at dozens of promising planets. That would be its own kind of discovery. It would suggest that Earth-like biology may be much rarer than we assumed. It would lend credibility to the rare Earth hypothesis. And it would raise the chilling possibility that the great filter is ahead of us rather than behind. Both outcomes are scientifically revolutionary. Both would reshape the field forever, and we will likely know which one we are in before the 2030s are over. For individuals alive today, this is a privilege almost beyond comprehension. People born before 1950 never had a chance to know. People born in 2050 may grow up in a world where the answer is simply taught in school, whether that answer is lonely or crowded. But we, right now, are in the exact window where the question still feels open and the evidence is arriving in real time. Every new Webb spectrum is a piece of the puzzle. Every biosignature candidate, confirmed or debunked, narrows the possibilities. Every world we eliminate, and every world we confirm, brings us closer to an answer that Fermi himself could only speculate about. 76 years after that lunch in Los Alamos, his question is finally starting to get concrete replies. The silence is no longer complete. Faint voices, maybe real, maybe imagined, are beginning to emerge from the dark. And whatever those voices turn out to be, we now have to wrestle with what they mean. So where does all of this leave us? After 76 years of Fermi's question, after 4 years of Webb's observations, after 32 chapters of hypotheses and evidence and argument, what can we actually say about our place in the universe? The honest answer is that we still do not know. But we know more than any previous generation, and what we know has quietly shifted the odds on each of the classic answers. If we are alone, truly alone, the only intelligent species in a galaxy of 300 billion stars, then every piece of evidence we have gathered is consistent with that. Red dwarf planets are often stripped bare. TRAPPIST, one's atmospheres, are mostly missing. The rare Earth hypothesis has gained new strength. The specific combination of conditions that produced us may be so improbable that it has not happened anywhere else. If we are hunted, if the dark forest is real, or if Berserker probes roam the galaxy, then the silence is explained. But our future is grim. Every radio broadcast we send into space could be pulling the trigger on our own extinction. The longer we last as a species, the more likely we are to eventually draw an unfriendly visitor. If we are simply early, if we are among the first intelligent species the Milky Way has ever produced, then the silence is no mystery. There is no one else to hear yet. Future civilizations, arising billions of years from now, will look up and wonder about the silence just as we do, and maybe by then, our descendants will be the ancient ones they are looking for. Each of these possibilities has evidence that supports it and evidence that challenges it. None of them can be ruled out, and each of them carries enormous implications for how we should live and what we should do next. If we are alone, then Earth's biosphere is the rarest and most valuable thing in the observable universe. Every species on our planet is a wonder that may not exist anywhere else. Protecting this planet is not just environmental policy. It is the preservation of something that may be, in the most literal sense, unique in all of reality. If we are hunted, then humility and caution are the only rational responses. Every act of broadcasting our presence is a gamble with our species' survival. Every decision we make about how visible to be on the galactic stage is a decision that could echo across millions of years. If we are early, then our responsibility is different still. We are pioneers. Whatever civilizations come after us, whether they are our descendants or alien successors, may look back on our century as the moment life first stood up and tried to see itself in the mirror of the cosmos. The patterns we set for peace, for stability, for longevity, may influence a galaxy's worth of history. There is one more answer that does not fit neatly into any of these categories. We may be surrounded by life simple, microbial, everywhere, and be simply in a narrow phase of galactic history where few civilizations exist simultaneously. The fireflies blink on and off. We happen to be blinking right now. Others blinked before us. Others will blink after us. The contact we crave may simply be a matter of timing, and the universe is not empty, just asynchronous. What we have learned, above all, is that the question is no longer purely philosophical. It is observational. Within our own lifetime, we will have data, real data, about real worlds that will tell us which of these answers is most likely correct. Webb has already started delivering that data. The Habitable Worlds Observatory will deliver more. Beyond that, future telescopes we have not yet designed will settle the question further. Fermi died in 1954. He never knew that 70-odd years after his lunch table question, a gold-mirrored telescope would sit 1 million miles from Earth, reading the air of a planet 124 light-years away, searching for chemicals that might be breathed out by alien life. He could not have imagined the scale of what we have built. He could not have imagined the instruments now being planned to succeed it. But he would recognize, instantly, the question they are trying to answer. It is still his. Where is everybody? For the first time in human history, we are close enough to that answer to feel it. Maybe in the next year, maybe in the next 5, maybe in the next 20, the universe is about to say something back. Whatever it says, we will never look at the night sky the same way again.